Hello everyone, my name is Vedatman Duhoon. I'm in Mr. Umit's 5th period linear algebra class, and today, the real-world topic I want to connect linear algebra to is balancing chemical reactions, specifically on how linear algebra and matrix operations can be used to efficiently balance those reactions. So, what do fireworks, medicine, and the oxygen we breathe all have in common? Well, they're all chemical reactions, and to make sure those reactions are safe, efficient, and not explosive, we need to balance them. But did you know you can actually use linear algebra to do it? Every chemical reaction follows a golden rule, the law of conservation of mass. What does that mean? It means that atoms can't just disappear or pop out of nowhere. Every atom you start with has to end up somewhere. Here's why this matters in chemical reactions. When you have products and reactants, the number of molecules and atoms on both sides must stay the same. That means that when you have the full reaction laid out, you need to balance both sides to make sure there are the same number of atoms on both sides. Otherwise, you'd be violating the golden rule. Now, the challenge with this is you need to balance complex equations like this, and oftentimes doing it by hand can be very tedious. It's easy to make errors, and there is a better way. The fundamental law means that every atom present before a reaction must also be present after, meaning it's a closed system. This means that with math, we can use a methodical solution to find an answer that is not error prone, or require a lot of time. Indeed, we can use a mathematical approach. In fact, we can use matrices. So let's talk exactly about what that process looks like. We represent each element in the reaction with an equation. Then we turn it into a system of linear equations, convert that into an augmented matrix, and solve it using row reduction. As you can see, if you follow these key steps, you will be able to solve these chemical equations in a less tedious manner and more scalable, consistent, and less error-prone manner. Alright, so now that we've discussed the theory behind using linear algebra to balance chemical reactions, let's put that theory into practice. As you can see here, this is a very common combustion reaction involving propane gas, the C3H8, with oxygen that yields carbon dioxide and water. So you can see that there are coefficients for each of these molecules, but we don't really know what these coefficients are, and we need to find them in order to have a balanced chemical reaction. So, how are we going to use linear algebra to do that? Well, the first step is to set up a vector equation that describes the number of atoms of each type present in the reaction. Since the equation involves three types of atoms, in this case the carbon, which is in green, the hydrogen, which is in blue, and the oxygen, which is in purple, the vector is going to be in R3. And we need to do this for each reactant and product that lists the number of atoms per molecule. So for example, in this first instance, you'll see that there are 3 carbons, 8 hydrogens, and 0 oxygens, which means that x1, the first coefficient, is being multiplied by this vector. In the next scenario, it is the same thing, except now there is 0 carbon, 0 hydrogen, and 2 oxygen, because remember, it is O2. And remember, because this is a chemical reaction where these are the reactants, and this is the product, they're both equal to each other. Again, by the golden rule, the law of conservation of mass. So, this is equal to x3 times 1 carbon, 0 hydrogen, and 2 oxygen, plus x4 times 0 carbon, 2 hydrogen, and 1 oxygen. Perfect. Now we have the vector equation all set up. Now, the next step we gotta do is move all the terms to the left side. So, in order to do that, I'll just be subtracting the right-hand side from the left-hand side. And as you can see, you're gonna get something like this. Minus, and then you take this side, and you're gonna, since you subtracted it from the right side is gonna have just 0. And remember, in this scenario, because we are moving this to that side, we're just going to be moving that negative into these vectors. That way, it just makes it look a bit cleaner because you're in addition everywhere. And again, you can do that because all we're really doing is just distributing out the negative sign. And if you do that, your new situation is x1 times 380, x2 times 002, plus x3 times 1, 0, 2 plus x4 times 0, 2, 1. But except, remember, because this is negative, these terms are going to be negative. And again, all we did here is move the negative sign and distributed it within these terms to make sure the coefficient remains positive, but the vector became negative. Cool. So now that we have this, let me just make sure it's negative. This is equal to 0, 0, 0. So we have this equation right here. How are we going to rewrite it? Well, we can actually consolidate all of the vectors here and rewrite it as 3, 8, 0, 0,